So as the title suggests, I'm going to talk a lot about computational assistance and artificial intelligence and its role in molecular discovery. Uh, as I go on, I'm also going to try to emphasize some of the complexities and some of the challenges that might pose subtle problems that require changes to how we approach molecular discovery from an algorithmic perspective. But just to start off at a very high level, I want to reiterate something that many people know, but some people might not appreciate, which is just the sheer breadth of applications that you can use small organic molecules to help address. So these small organic molecules, like the one shown on the slide, are a very, very versatile modality. They make up the majority of the FDA-approved medicines in the US, but we also use them in agriculture. We also use them in materials. We also use them in defense applications. And really, even though it's the same, elements and atoms being rearranged in different ways, right? The diversity of functions that can be achieved is quite impressive. And so what really interests me, and a lot of what the group is focused around, is thinking about how we sort of anticipate and design these properties and what really the process is by which we can arrive at these structures. The process by which we would identify that Ritalin might be a good therapeutic intervention for ADHD is similar in some ways to the process that we might use to arrive at DDT as an insecticide or insect repellent. But obviously the details change, but the overall design will be kind of similar. And so it's really this design workflow that organizes many of the themes that I'd like to think about. So in the pharmaceutical industry, we might just see a cycle that says design, make, test, analyze. Here it's much the same, just a little bit elaborated. As we sort of go through the process of molecular discovery, we've defined some goal or some set of functions we might want the compounds to achieve. And in therapeutic spaces, maybe that relates to potency, bioactivity. For materials applications, maybe that relates to some optoelectronic properties. But with that goal in mind, we design structures. We hypothesize what molecular structures might satisfy those design goals. With those designs, we go into the lab, we make them, we test them, and we get information. And usually we just take that information, we feed it back into some sort of models, whether those are sort of expert qualitative models or whether they're quantitative machine learning models. And that helps inform the next round of design. And some number of times iterating through this cycle might let us arrive at new small molecules that perhaps have the functions we want and meet all of our design criteria. And so this is how we'll sort of organize the talk today. The questions we might ask in the modeling stage would be connecting molecular structure to function, a very classic task, but one that still has ongoing complexities. We can think about molecular design and proposing new structures, right, as we iterate through the cycle. Synthesis, right, which is figuring out how to make it, right, go from a whiteboard to the laboratories is not an easy feat necessarily. And there's some additional work that I won't cover in detail today related to analytical chemistry and structural elucidation, but we'll save that for another time. So overall, this workflow is an optimization. It's an iterative process. It's decision-making under uncertainty. And for that reason, it's quite helpful to have some computational assistance as a framework. So we're going to start off with modeling and thinking about that very classic problem of structure-property relationships. So models have been used for decades and decades to help connect structure to function, and we typically would think about training them on experimental data. So we might have a list of molecular structures and some property of interest. Maybe again, that's a potency or a binding affinity. And the goal is to build some sort of understanding of how structure relates to that property so that we can firstly screen new molecules for which we don't have experimental data and predict their properties, find which ones are the best according to our model. We can also do the same thing for simulated data. And we've seen a lot of great successes of this in the context of electronic structure theory or other computational chemistry pipelines, where we could simulate the properties or estimate the properties of a molecule with maybe CPU minutes or CPU hours. But if we train a model to sort of recapitulate the results of that simulation, we might be able to get that prediction in milliseconds. And so that lets us address larger systems or higher throughput applications of those tools, which is also quite helpful for molecular discovery. Now, connecting structure to function is a nice idea, but when it comes to implementation, you start to encounter many different decisions about how you represent that structure and how you learn that relationship between structure and function. And so there's really a zoo of different molecular representations and different surrogate models that can be used to build this relationship and build these sort of understandings. To some extent, it depends on the kind of information we're trying to capture, whether that's just an aspect of the chemical formula or all the way up through three-dimensional confirmation of the structure. And sort of depending on that choice, we might choose different numerical representations for our molecule. Structural fingerprints are quite common that sort of capture the presence or absence of certain functional groups. Graphs are also common, as we'll talk about, but there's language representations as well. These smile strings, people have used Coulomb matrices of voxel representations and three-dimensional sort of point clouds as well. And all of these have their use cases. And all of them are compatible with different choices for the regression architecture, like the model itself. So many of you will be familiar with the sort of standard machine learning pipelines, random forests, neural networks. For graphs, what's best suited tends to be these message passing neural networks. And so we'll dig into that a little bit in more detail because that's one of the representations and models that we spend a lot of time with. So fundamentally, right, the idea is that one representation of a molecular structure is as a graph. The atoms are nodes in the graph and the bonds are edges in the graph. And this concept has been applied for 150 years, originally not with the goal of training neural networks, but with the goal of counting the number of possible molecular structures that satisfy valence rules. So in the 1800s, it was sort of in vogue to estimate the size of chemical space, still kind of is today. And so you can see in this sort of snippet that the idea was that you define a diagram as a set of points, those points having sort of elemental identities. You have constraints on the number of linkages going through each point that corresponds to what we now would call valence rules. And they use this to count the number of possible structures they predicted to be stable. And so this is, I think, before people actually called graphs graphs. Now we would just say, oh, it's a molecule, it's a graph. And today, most of why we would represent molecules as graphs could be for these applications to graph neural networks. So graph neural networks can learn to take this structured data as input, features of the atoms, features of the bonds, and learn to convert this into some predictive property if we give it sufficient training data. It's a normal sort of supervised learning formulation. And so I already mentioned message passing neural networks, these MPNNs. That's a very popular architecture choice for working with molecular data. So when we apply MPNNs to graphs, the basic idea is that we'll start off with some simple features describing each atom and each bond. What we'll do is over the course of multiple iterations or convolutions, we will allow messages to be sent between atoms, and we can update the representation at each atom to sort of enrich its local chemical environment. So in the very beginning, if I'm looking at the features associated with this OH, right, this hydroxide on this carboxylic acid, all it knows is that it's a hydroxide. After one round of message passing, it learns a little bit about its neighbors. And it starts to recognize that in this context, part of a carboxylic acid motif, it's an aryl carboxylic acid as well. And over multiple iterations, you enrich that vector that describes that chemical environment. So you can train this sort of end to end to predict different physical properties, different chemical, biological properties. What it will do is it will learn how to fine-tune those messages for the task at hand. And this works very well. I want to emphasize that it works very well in most cases, especially in these data-rich regimes. Maybe you've got more than a few thousand data points. They tend to work fairly well. The problem, though, is that graphs actually aren't sufficient. Right? Thinking about molecules as graphs feels very natural, but then you start to realize that there are some subtleties that might cause complications. So the most basic problem that you might run into is the problem of stereochemistry. So two enantiomers, as shown here, are mirror images of one another. They're not superimposable by translation and rotation. They have identical graph connectivity, and we can't tell the difference between them if we use a normal graph neural network. There's also questions of sort of how you represent different sort of bonding structures and patterns. And so having tautomers and resonance forms and aromaticity also provides some ambiguity in representation. And so in this sort of example that I'd like to point to of this sort of 2-hydroxypyridine, if we have either N or O alkylation, depending on sort of which form we've started with and which form we end with, we'll have a very different view, or the model will have a very different view of what happens during that reaction. It will look like we've sort of converted this hydroxide from a single bond to a double bond, but really this exists in sort of an equilibrium. And so that will lead to some ambiguity and confusion in the model. Other challenges relates to the fact that there are many, many more interactions beyond just simple covalent bonds. And so when we start to think about organometallics or even salt forms, where the salt might be localized to sort of free base amine, that is not something that is well captured by the sort of covalent bond graph. Similarly, right, to the stereochemistry in the first example, stereochemistry gets much more complex even, and something like H-drop isomerism, which is quite abundant in many sort of therapeutic applications, many catalysts. That's not something that graphs capture at all. It's not something that really the language for encoding these structures tends to capture at all either. And so there's a lot of complexity left to address in this representation challenge. Now we'll focus for a moment just on the question of tetrahedral chirality and those two enantiomers that were not superimposable mirror images. When we think about symmetries, we can think about the sort of physical symmetries that exist in the world. So if I were to represent a molecule not as a graph anymore, but as a three-dimensional structure where each atom has specific Cartesian coordinates, and so we have bonds, angles, distances between atoms and dihedrals defined for this structure, processing a three-dimensional representation with a three-dimensional neural network designed with E3 invariance or E3 equivariance means that that model, basically an E3 invariance model, would ignore translations, rotations, and reflections that exist in sort of three-dimensional Euclidean space. And so if we have two molecules that differ by a reflection, those can exhibit very different properties, but yet an E3 invariant model can't tell the difference. And so we think about other symmetries. Maybe we want our model to ignore the translation or rotation of the structure because it's the same structure, but be sensitive to reflections. And so SE3 networks can do that, but they also will be sensitive to small adjustments in angles and dihedrals. And so that prompted us to develop a different kind of network, a network that has the symmetries we want and doesn't have the symmetries we don't want. So we call this Cairo. And so Cairo is essentially an SE3 model that also adds this sort of inter-roto type invariance. And what that means is that if we were to take two enantiomers of each other that only differ by that tetrahedral center, and if we were to sort of spin around these single bonds, it's the same structure. The red molecule is still the red molecule. The blue molecule is still the blue molecule. They're still not superimposable. But we want our model to recognize that one conformation of the blue molecule is the same as another conformation of the blue molecule, because it's the same molecular identity fundamentally. And so that's what Cairo does, is it embeds the molecule and encodes their three-dimensional structure in a way that doesn't distinguish between rotations around these rotatable bonds, these changes in dihedrals. So it does that in a way that means we can take one of the molecules and we can spin around this bond and it's the same representation, but it's different than the enantiomer when we spin around that bond. So again, it's sensitive to chirality, but it's insensitive to rotations of dihedrals. So it's the same structure. So what this ends up looking like is if you were to take a set of conformations of the blue molecule and red molecule, there's only two unique chemical structures in this slide. We're just enumerating different conformations of those structures. We can see that these sort of E3 invariance models, Schnatt and Diamond++, when we sort of have many different conformations of each, they learn to put them in the same place. Essentially, they can't distinguish between the blues and the reds. An SE3 invariance network like SphereNet can. And so you can see that it is able to learn how to separate, for the most part, the blue molecules and the red molecules, which are the same structures. Within each color, the same structures. And then sort of by design, what Cairo is doing is it's mathematically treating all conformations of the red structure as identical and all conformations of the blue structure as identical. And so you get this perfect separation in its learned latent space where it knows these are different molecules, but all conformations of red are the same molecule. And so this is, a very specialized way of representing molecular structures, but one that is, in my opinion, at least, better suited for molecules that exhibit tetrahedral chirality. So there's, again, more challenges to address in representation, but at least we're starting to see some progress in our ability to model chiral structures and understand the role of tetrahedral chirality in molecular properties. So we're going to move on from property prediction and modeling to design. So we are going to think about now the design of new molecular structures. Typically, the way that we've mostly approached discovery through computational assistance has been with virtual screening. So virtual screening is the very standard approach of taking these enumerated or sort of full lists of candidate structures and running them through some sort of experiment or simulation to evaluate their performance, and then picking the one that's the best. So we just screen all the structures in that list. And so these virtual libraries essentially form search spaces. If we view the whole molecular discovery problem as a search or an optimization, this is saying that the design space that we have to work with is the list of chemical structures. And so we can go online, we can download large catalogs of compounds, and we can pose molecular discovery as this task from a finite list. Now, where there's been a lot of interest, of course, is in the use of generative design and thinking about how one can use models to not just help us evaluate structures, but to propose new chemical structures. We propose the new chemical structures that are predicted to have the best property. And so this is quite appealing because generative models seem to be able to explore a very large space. They're not limited to just the molecules that we happen to list out in the virtual libraries. And so with generative models, we have the ability to potentially be much more creative. And so we'll talk a little bit about virtual screening, and then we'll move on to generative design. Because virtual screening also has opportunities for improvement. I described virtual screening as this sort of exhaustive evaluation of candidate structures, and that's typically how it is applied. So if I have a list of 100 million molecules, and I want to know which is the best molecule in terms of its predicted binding affinity to a protein of interest, I might take those 100 million candidates and I might dock them, right? This sort of coarse simulation of protein ligand interactions. I might say, let me dock 100 million structures and find what the best one is. Well, instead of doing that and spending a lot of time on 100 billion simulations, we can insert a model into the workflow. And we can use model-guided Bayesian optimization to say, let's not evaluate 100 million. Let's evaluate a few. Let's train a model. Let's use that model to predict the performance of the rest. And then select the ones that are worth evaluating with docking. Because trained machine learning models can typically work very fast compared to this docking analysis. So if we can evaluate our library in a millisecond per molecule, as opposed to docking, which would take maybe multiple seconds per molecule, there's a large speed up to be realized. And so this application of Bayesian optimization is a pretty direct extension of the Bayesian optimization you might be used to in continuous spaces and in terms of one-dimensional scalar functions. When the sort of classic 1D case, what we do is we compare, or we sort of evaluate the landscape where maybe we have some model with this black line, we've got some uncertainty in the shaded region, and we define some acquisition function, which tells us, based on our model prediction and uncertainty, what's the most promising location to acquire a new observation. And so this sort of scalar view on the right indicates that classic case, and All that changes when we're talking about chemical space is that we don't have a continuous line that we're choosing from. We have a big list of candidates, but we can still use the same principles, the same notion of acquisition function to select the most promising regions of chemical space. And when we do that, we are finding a pretty substantial acceleration in the ability to find the best performing molecules. So this is using those 100 million structures as candidates. And here we're looking at the performance, or the percentage of the top 50,000 structures that we're identifying as a function of how many ligands we've simulated, right? How many tests we've run. And what we can see here is that if we use a message passing neural network shown in green as that surrogate model, then actually with 2.4 million simulations, so 2.4% of the space, we're finding 90% of the best molecules. And so using these models to help us triage chemical space and point us in the right direction is a quite powerful approach. And it leads to these orders of magnitude accelerations in simulation. Now doing this, right, this notion of Bayesian optimization does require, to some extent, uncertainty estimation. So typically, we don't just want to ask our models to make a prediction of a property or of a docking score, but we want them to predict the confidence or the error as well, because there's value in exploring regions of chemical space where the uncertainty is high because it might contain strong performing compounds. Now, uncertainty quantification is very challenging. It's a task where there are a lot of approaches and fairly inconsistent performance across different tasks and data sets in chemical spaces. So some of the more common approaches you might be familiar with would be sort of deep ensembling, or maybe we simply just train multiple randomly initialized replicates of a neural network model and we use their agreement or disagreement as an indication of uncertainty. There's also approaches of distance to training sets, trying to sort of use neural networks and random forests together. There's a lot of different variations of how we approach this. And one of the methods that we explored a couple of years ago was the use of this technique known as deep evidential uncertainty. And so what deep evidential uncertainty does is it doesn't ask our model to just predict one value given a molecular structure as input, but to predict 4. And those 4 values together parameterize a distribution that describes the model's prediction and its uncertainty and the uncertainty of those predictions themselves. And so the sort of evidential approach, what we were able to do was show that, yes, quantitatively it looks quite promising in some standard benchmarks, but also if we were to reanalyze this virtual screening data from the Stokes et al. Paper in Cell where they were doing antibiotic discovery, using evidential uncertainty could have helped us increase the experimental hit rate. So if we'd taken the highest performing predicted candidates and we looked at the confidence of the model and we had said, let's only test the molecules for which we are most confident, we could have had a nearly perfect experimental validation rate. Already it was quite high, but confidence, according to the model, did correlate in this dark blue line with the likelihood of whether that prediction sort of bore out in experimental testing. So virtual screening, again, isn't sort of a static workflow. It's something that we can insert models into, and we can benefit from all the approaches and techniques in uncertainty quantification and property prediction. And we can even continue it and continue this idea of Bayesian optimization to save even more computational cost by recognizing that over the course of an optimization, there's some molecules that are going to look promising and we want to test them. Some molecules that are going to look okay, and so we want to keep them in consideration, but not test them yet. But some molecules that look so bad that we don't think they will ever be competitive with the best structures, we can actually remove those entirely. And this gives us another maybe factor of 2 computational speedup. And we see in this sort of complicated bar chart that we don't actually lose any performance. That's all this is saying. If we do model-guided Bayesian optimization with this pruning step versus without the pruning step, we basically get the exact same results. And so now these collections of virtual screening approaches let us access larger and larger design spaces. And so now we can think about screening hundreds of millions or billions of compounds with the use of models to help us save some cost. But that's just virtual screening. And again, that's just the approach where we take some simulation or some model and we query it with the structures of interest. Generative design, again, was the notion that we can take this structure property relationship and invert it in a sense and say, well, I want to know what structure exists at this maximum. And so generative design has gotten a lot of attention. It's a very broad class of techniques that proposes new molecular structures in this context. And the way it typically works is we will have some database of molecular structures and we'll teach a generator how to propose molecular structures that look reasonable. Then we'll use those proposals and feed them to an evaluator or a scoring function. And that scoring function is going to provide feedback to the generator based on how good or bad those structures look for the given task. And so as just an example, we've, in this example, trained a property prediction model as the evaluator to predict the efficacy of a molecule as a protein degrader. Just using some public data, we didn't do any validation of this experimentally. But given the evaluator, this generator, which is a graph-based generator proposing molecules atom by atom, has learned to propose this new structure, which resembles very closely some real protein degrading molecules. And so, of course, this is the kind of structure that we would then move on to testing experimentally. Generation can happen as a graph, as I just showed you, or it can also happen in three-dimensional space, right, as this sort of explicit shape-based and shape-aware conditional generation. So this is an animation showing the results of a model that's been trained to take this blue mesh as a query and propose a chemically distinct molecular structure that approximates its shape in a volumetric sense. And so you can see we have this sort of 3D generation now where it's not just the connectivity, but it's also the conformation that we're proposing. And there's really a very wide range of approaches that people can use for molecular design. And it's sort of hard to overstate the number of different approaches that have been proposed over the years using language models, using graph models, using this sort of differentiable graph representation, even where we directly take the derivative of a property of interest with respect to structure. So even though molecules are discrete, we can sort of trick the model into taking derivatives and use it to sort of climb the hill and maximize the property of interest. It's not even just the sort of single property that we can ask our generator to optimize. So in this feedback loop of evaluation back to generation, we could have many, many different properties that we're trying to improve. And so we can use concepts like Pareto optimization to try to propose new structures that have these optimal properties for many, many different criteria. And there's several different ways of doing this. If you're interested in this, I'd encourage you to look at this review article in Patterns. And really the sort of simplest way to describe it is, we can imagine over many iterations, sort of enriching the chemical space of molecules that we're generating to be closer to this Pareto front of non-dominated points, where we have these sort of perfect trade-offs between objective 1 and objective 2, where we can't improve one without worsening the other. Again, many different ways of approaching this. They've all been used. They've seen different levels of success, but it's really a rich framework for molecular design and generation. Now, it's not all good, right? If you look at how these have been applied in practice, one of the challenges that the field runs into using a number of these different design techniques is that sometimes the creativity of models is a bit much. And what I mean by that is that sometimes when you take these generative models and you ask them to optimize a property of interest, you see this sort of issue where you get structures that are highly nonsensical. They're not particularly stable. They're certainly not synthetically accessible, and they're just not useful, right? They're structures that maybe maximize what the evaluator thinks is a good molecule, but that doesn't match what a chemist would think is a good molecule. And so there's a sort of misalignment between the structures that are being generated and the types of structures that are actually useful to us as chemists. Now, for those of you that might have worked with generative models for molecules, you might think, well, I can train a variational autoencoder using a smile string representation, and it will propose molecules that look fairly reasonable. And you're right. If you're just proposing molecules for the sake of proposing molecules, you can often get structures that look very sensible. And here, sensibility might mean synthesizability. So if you train your model on a database of structures that are mostly synthesizable, the structures you get will also be mostly synthesizable. The challenge is when you ask these models to optimize. So when you ask the models to optimize and improve or maximize a property of interest, that's when they sort of get pushed into very strange areas of chemical space. Now, to address this, sort of we and others have thought a lot about synthesis and how we can also use computation and AI to help us plan the recipes for making chemical structures. And just to reiterate why this is so important, right? It's really our understanding of chemical synthesis and reactivity that lets us successfully apply these computational approaches to molecular design. So on the left, the virtual libraries that we would screen in those really high throughput virtual screening campaigns are generated through reaction transformations that we think we can run. On the right, we've seen a few of the ridiculous structures from generative models, and sometimes they propose things that look okay, but sometimes they propose things that look not okay. And so, of course, no matter what, we have to find routes to make these new structures. And so there's a lot of different opportunities in this space, and AI for synthesis is a rich field of its own. We've sort of written about this both for organic and inorganic synthesis in the past. The sort of foundation for everything that we will do is going to be data. So having accessible and searchable data is really a good foundation for using AI to help with synthesis. But we might then want help acting on that data and analyzing that data. And so we might imagine these sort of virtual laboratory assistants that we can interact with and help us troubleshoot, right? Like an expert chemist in a lab could do. Now, eventually, we'd like to use sort of an understanding of chemical synthesis to reach this ultimate vision of having full digital twins or, simulators for the chemical lab and these autonomous laboratories where we combine robotics and AI-driven planning. So this is sort of what we're pushing to, and maybe we're not fully there yet outside of proofs of concept, but we're at least in this middle stage of developing virtual lab assistants. So thankfully, a lot of the data aspects have been not taken care of, but helped by commercial publishers like Chemical Abstracts and Elsevier, who have curated these large tabular collections of reaction data over the years. So this example is from Reaxys. We mostly work with Chemical Abstracts data from SciFinder these days. But what you see in either case is tabulated entries that record the reactant structures that were used, the major products that was reported, some aspect of the conditions, some metadata of who ran the reaction and when. And so you get this sort of snapshot of that chemical reaction, the piece of information that it conveys. Now, in these entries, you don't have everything that you might want as a chemist or someone trying to train an AI system. We don't have tabulated data on concentrations. We don't have tabulated data on the vessels that were used, flask or vial or well plate. Orders of addition matter, but aren't typically recorded. And we also don't have full characterization of the outputs. So typically you wouldn't report byproducts and minor products. And there's a huge bias towards high yielding reactions. And so we rarely see low yielding reactions. But we still end up with this collection of millions or tens of millions of reactions that we can train models on. And we've done this. And I won't be going into a large amount of detail due to time, but suffice to say that, in the 70 years since computer-aided synthesis planning was first proposed and developed, there's been a lot of progress, especially in the use of data-driven synthesis planning. And so this is an example output from the ASCOS program, where we've queried it with this drug substance. We've ended up with this large network of possible pathways. So each one of these little branches represents a different way that we might make this molecule, with some suggestion of the viable materials, the conditions, intermediates along the way. So for those of you sort of in this space that might benefit from such a tool, I should mention that ASCOS, the software that I mentioned in the previous slide that has been developed out of MIT for several years now, is open source. There's actually a brand new open source release on GitLab. It brings together a lot of different tools for retrosynthesis, condition prediction, product prediction, some tools for reaction classification and atom mapping. There's really a broad range of tasks that it can help with. And some of the targets that you'll put in, if they're very complex and don't resemble the training set, it's true that you might get few suggestions or no suggestions. But for some molecules of moderate complexity, it's a fairly rapid way of coming up with ideas for their synthetic preparation. So I'd encourage you to check it out. Again, the full sort of source code is open source on GitLab. Now, it has a certain range of capabilities. It looks at sort of retrosynthetic analysis, product prediction, all of these sort of reaction deployment tasks as described on this slide. Where we'd really like the fields to go in using AI for synthesis, and AI for synthesis to help discovery specifically, is towards the right. Over here, thinking about maybe new method development or even identifying sort of novel catalysts or ligands that can help us achieve transformations between structures we couldn't otherwise react with each other. And to sort of push ourselves from simply just using known reactivity in new contexts on new substrates to developing new reactivity, we think that we're going to benefit from some improved data structuring and data sharing. And so that's where this effort called the Open Reaction Database partially comes in. So the ORD is an open access resource. Its goal is to support machine learning in these types of models that will enable better prediction of reaction outcomes, better design of new structures. And it's meant to provide both a data structure, but also a database of reactions submitted by chemists that reflects the sort of breadth and diversity of chemistries that are used in the field and captures details of the procedure with more nuance and more detail than has been done in the past. So I encourage you to look at the Open Reaction Database as well, if you're somebody that either produces or uses organic synthesis data. So in just the last few minutes, I want to briefly mention another line of research that is trying to actually combine aspects of molecular design and aspects of synthesis planning together. As I sort of presented them, there are two different steps. We use generative AI to propose new molecules, and then we do synthesis planning to say, can we actually make them or not? But there's an opportunity to align these two. So generative design typically works on these SMILES strings, character by character, or graphs, atom by atom, or sometimes in 3D or fragment by fragment. But instead, we can conceptualize the design of a molecular structure as the design of a synthetic pathway. So when we do that, we're designing new molecular structures reaction by reaction. And so we can actually teach an agent, a machine learning model, to generate the structure of a synthetic tree. We do this as a conditional generative task, which means we take in this sort of vector encoding of the kind of molecule we want, and the agent has learned to select commercially available building blocks and select reaction transformation rules that build complexity and get us to a full synthetic tree, which implicitly encodes the product molecule. So it's like, instead of designing the structure you want, you design the process that you will use to make a structure. And so This framework can be wrapped with different optimization algorithms. In this case, we just use a genetic algorithm. And so if we change that input code, we change the pathway and we change then the tree and then the product and the properties of that product. And so we can apply it to optimization. We can apply it to maximize some predicted bioactivity score. We do this with our model that I'm showing on the slide, as well as a number of other models that operate on atoms or fragments. And one of the sort of consequences of proposing molecular structures as the proposal of their synthetic routes is that everything is guaranteed to have a pathway. And there's a bias then towards shorter pathways. And so in this case, actually, the molecule that is proposed by the model just requires a single synthetic step. The other molecules that are proposed by other models that don't think about synthesis aren't particularly attractive, stable, reasonable, and posed a different way, they would not be synthesizable. You would not succeed in trying to make these. Whereas we have this very straightforward molecule to make using this model because we're forcing it to think about synthesis along the way. And so this model, which we've called SynNet, right, is a generative model that knows about chemistry, and it's searching a chemical space that is synthetically constrained. That's kind of like these virtual libraries. But instead of enumerating billions or more of these structures, that full chemical space just sort of lives abstractly in this generative model, and it can explore it on the fly as it needs to for different tasks. The issue that we're starting to run into now, thinking about applying these techniques to therapeutic discovery, to catalyst design, to ligand design, is that scoring molecules is arguably a harder task. So the really weird structures that I mentioned generative models providing don't arise out of nowhere. They arise because the scoring functions or the evaluators that are being used to critique them have these pathologies. They have these sort of like little holes, little quirks that these optimized generative models can exploit. And so the generative model finds these really weird ways of achieving a high score that doesn't align with what we want. And so improving our ability to score and evaluate proposed structures is a really tremendous opportunity for the field, and where I think a lot of increased attention can be placed. All right, so to summarize some of the message that I hope you've taken away from today, using AI for molecular discovery is essentially trying to coordinate and orchestrate and accelerate this complex map of maybe molecular design, experimental ground truth, some computational models, some different machine learning models. And throughout this whole process, we encounter some consistent challenges and opportunities. So, at the end of the day, experimental evaluation is going to be the ground truth. That's going to tell us if this molecule actually does what we hope it does. When we use models to help us prioritize structures, we have to think a lot about molecular representation. There are many approaches that work well, but there are few that fully solve the problem, if any. Virtual screening is sort of a very compatible framework with Bayesian optimization. And so we can use model-guided optimization to explore larger chemical spaces or explore chemical spaces faster than before. If we want to use generative AI, it can be very creative, and that's empowering, but it can also lead to suggestions that don't look reasonable. And so we can use generative AI, but designing structures in terms of their synthesis. And so designing in synthesis space instead of structure space is one way of guaranteeing that we get proposals that we can take into the laboratory and actually test. And with all of these tools, right, to help us along the way, it's important to keep in mind that generative AI and generative design is not a panacea, that you really do need scoring and evaluation functions to help us sort of look in the right direction. And so improvements to these are very much needed across basically all applications, I would say. So I'll end by acknowledging the research group that we have at MIT, acknowledging sort of generous funding support from a number of different agencies and companies. And in particular, a lot of our work geared towards therapeutic discovery has been with the Machine Learning for Pharmaceutical Discovery and Synthesis Consortium. And I'll thank you for your attention and joining us today, whether it's early morning or late evening. I'm happy to answer some questions in the Q&A.